Yeah, just have explained before. So, if we call it as a two-dimensional nanomaterials, if I call it as a, so let's check whether it is recording or not. Yeah, perfect. It is recording. Yeah. So, just like I explained before, the two-dimensional nanomaterials in which the two dimensions are not confined to the nanoscales. So here you can see the length and the breadth. Like I said, the Lx and Ly, which are two dimensions, like x and y axis, they are more than 100 nanometers. But what about the thickness? The thickness is less than 100 nanometers. So if two dimensions are not confined to the nanoscale, that is called as a two-dimensional nanomaterial. The same goes with one-dimensional nanomaterial. If one dimension is not confined to nanoscale, it is called a one-dimensional nanomaterial. Here, the 3D, the no bulk dimensions of nanoscale. I mean, the three dimensions, all the three dimensions are not confined to the nanoscale. So this is called as a three-dimensional nano. So we don't actually call it. I mean, there are different definitions which I will explain it later in the next slides. You will understand why we still call it as a three-dimensional nanometer. Now it's just a follow-up of the first slide. So yeah, it's just a follow-up of the first slide. We have zero-dimensional nanomaterials where all dimensions are nanoscale. Where you can see here it is x, this is the x-axis, this is y-axis, and this is z-axis. So in zero dimensions, all the three dimensions are not confined more than 100 nanometers. But in one dimension, see, if you consider only one dimension, you can see this cuboid type. It's like a long one. Here, either the x or y or z, which is not which is not confined to the nanoscale. So it is called a one dimension. Now let's come to two dimension. Two dimension is like a slide, or you can as a rectangle or a film, which has the two dimensions are not in a nanoscale, but the thickness is in nanoscale. That's why we call it the two-dimensional nanometers. Now let's come to three-dimensional nanometers. All dimensions, no dimension of nanoscale. I mean the all dimensions at the micro scale. So as I've said before, why we still call it a three-dimensional nanometer, I will explain in the next slides. So these are the few examples to just follow up. So the gold nanoparticles. I mean, if you make nanoparticles from gold, so what do we call the gold nanoparticles? Because they are made from gold and their dimensions, all three dimensions, the x, y, z, are all confined to nanoscale. So we sometimes, if all the three dimensions are less than 5 nanometers, we sometimes call them quantum dots. There are different wide variety of classifications in zero dimensional nanometers itself. So one variety is a gold nanoparticle where you can see all the three dimensions, just like a sphere, very of a radius like diameter of like 10 or 20 nanometers or 100 nanometers. And this is for the zero dimensional nanomaterials. We call it 0D. Now coming to CNTs. So CNTs are nothing but carbon nanotubes. There are different ways we can make, where we have a PVD, physical vapor deposition, and chemical vapor deposition. There are different process to which we can form CNTs. But we will come to that later in the like production techniques. For now, let's just focus on the classification. So in CNTs, we have CNTs are nothing but carbon nanotubes, and there are different types of CNTs like single wall, multi wall nanotubes. For the picture that I'm showing here is a single wall. I mean the only one wall, right? See, you can only see this single wall. There's only single wall. That's how we call it a single wall nanobit. I mean, there is only one wall. If there are other walls, like if there is another tube inside a tube, then we call it multi-wall CNTs, because there are multiple walls. So for now, let's focus on CNTs. In CNTs, there is the diameter is like in the range of 10 20 nanometers or 50 nanometers, depending upon the type of production technique we are using to produce CNTs. Here, for example, here I have shown the x and y axis. I mean, hole covers the diameter. So the x and y axis are like are in the range of nanoscale, like less than 100 nanometers, but length, which is greater than 100 nanometers, so it is called as a one-dimensional nanometer. Now coming to the two-dimensional nanometers, which I have shown is a thin layer. Now, see, the x-axis and the y-axis both are greater than 100 nanometers. But what about the thickness? Thickness is less than 100 nanometers. So we call it as uh, uh, a thin layer. So just like that, if there is a question like uh, what is the dimension in which we call it as a nanomaterial? We just really say if you have if you have a material, if one of this dimension is less than 100 nanometers, we call it as a nanomaterial. Now coming to surface to volume ratio, see, let's go to yeah, we'll start with this line. So what's happening here is like see, you have a cube. It has x, y, and z. It has a x, y, and z. So it has three sides. It has sorry. It has a for in this view we can only see three sides, but at the back front there are also three sides. So the cube has six faces. So if I assume that this small cube has an like uh, side of length a. So how many cubes there are? There are three, and three. There are three. Three is nine. So there are nine cubes, and finally, how many are there? There are like surface. We have three square and six, which is equals to 54. So 54 into a will, if I take a as a 1 centimeter, then 54 into one is equal to 54 centimeters square. But what about the volume? Volume will give say three cube, which is 27. A is equal to one, like a cube is 27 cube. So surface to volume is surface area divided by volume of the cube. So that is 54 by 27, that equals to 2. Now what I did is I removed this part of the cube. I removed these parts of the cube, and I just took this part of the cube. Like, see here, there are like 1 2 3 4 5 6 sorry, 1 2 3 4 4 to the 8. There are 8 small cubes. Then if you do the calculation, like finding here the surface area and finding the volume, you will get the surface area by volume is equal to 3. Now if I take only one cube, see, it has six faces. So one square, I mean a into a is one square into 6 is equal to 6, volume is equal to 1 cube. So surface area to volume is equal to 6. See, if I started to decrease the size of the particle, I mean, if I just disintegrate the whole material into small particles, the surface area to volume will increase. So, for example, I'll just show here. See, if I have a sphere and I have particles in it. Uh, for example, this is assume this is a nanomaterial or a bulk material. For example, assume this is a bulk material. So see, inside the bulk material, the number of atoms. But what about on the surface? Surface have less number of atoms when compared to bulk. If we when we compare to inside the material, if we are talking about the bulk materials, what about if I started to decrease the size of the material? What if I started to decrease the size of the material? See now, the volume, I mean the number of atoms inside the material started to decrease. But what about the surface? What about the surface? The number of atoms on the surface are increasing, because if you make smaller pieces of a big, suppose if I have a big material like a chalk piece, and then I make a powder, so which has a higher surface area, because when you make or disintegrate the material into smaller parts, the surface area which was hidden inside the material when it was a whole piece, like whole bulk piece, that comes out. So if you decrease the size of the particle, the surface area comes out. I mean, the atoms which are hidden inside the material, I mean the surface area which was hidden inside the material, comes out. So if we reduce the size of the particle, the surface area increases. In turns, the number of atoms on the surface increases. So these are the different shapes. Here I have like a sphere and cylinder and cube. So for example, if I take a sphere, it has surface area which is equal to 4 pi r square, and the volume of the sphere is 4 by 3 pi r cube, and the surface area by volume is equal to 3 by r. And same goes with cylinder. Area is pi r square h, volume is 2 pi r h, and surface area by volume will give us to 2 by r. And if I go with cube, which has surface area is equal, if I assume that see for example here, yeah, if I assume this is diameter and it has radius 2r, and it has height h. So if I take diameter 2r and height h, the surface area will be pi r square h and the volume is 2 pi r h. It is 2 pi r. And same goes for cube. If I assume the side length L, then area will be 6L square, because each side will have length L, then the area will be L square. So there are six faces, which is 6L square, and volume, which is length into breadth into height, that is length as it is cube. So length and breadth and height are equal, so it is L cube. So when you divide A by B, it will give by 6 by L. Now, just like I have said before, see, if I started to reduce the dimension of the nanomaterial or any material, if I started to disintegrate and started to reduce the size of the material, what happens? The fraction of surface atoms will comes out. See, for example, I will draw again. Suppose this is a bulk material and it has many like particles in it. There are many particles inside the material and there are many particles on the surface of the material. What happens if I break or if I disintegrate into many pieces like this? Now see what is happening. So if I take this single one, see. So if I take this single particle, see, if this single particle, if I can put it inside the material, so what happens if I put it again inside the material? These the surfaces, these new surfaces will get hidden. So if I disintegrate this particle, these surfaces comes into picture. So what happens here? The number of particles that is inside the body are now decreasing. The more and more atoms or more and more the particles on the surface are coming into picture. So if I started to decrease the size of the material, or I can say the nanometer, the dimensions are in nanometer. If I started to decrease the size of the material, what happens? The surface atoms, or the y-axis is the fraction of surface atoms. That means the surface atoms, the fraction of surface, the formula for the fraction of surface atoms F is equal to the atoms. Sorry, the atoms on surface divided by atoms in the bulk or inside the volume. So it's nothing but the surface by volume ratio. So the if surface is increasing, what happens? The number of atoms on the surface also increases. So that's what is happening. So if I start decreasing the number, like going down in the dimensions, like I start with 1 mm, 1 micrometer. If I start with 1 mm and I came to 1 micrometer, I mean if I have a 1 mm cube material, and if I started to do disintegration, and once I achieve the disintegrated powder one, the disintegrated size of the material is 1 micrometer. So what is happening? See, the fraction of surface atoms has increased from like 0.0 10 to the power of minus 4 to like 0.1. What happens if I goes to nanoscale, like 1 nanometer? See, the most of the atoms that are there are now on the surface. I mean, the more than like 99%, all the atoms in the material are now on the surface. So the next paragraph, so the next diagram here, the next graph also represents the same. See, If I reduce the particle diameter, now we are talking in the nanomaterial, nanoresin, like 20 nanometers. The particle diameter starts from decreasing from 20 to 5 nanometers. So why there is a drastic change in the surface atoms, like it is reaching to 100%, like approximately like 90-95%. Why the most of the atoms are coming onto the surface? Because see, if I take like bond, what is the like distance between the atoms, like well, it is the lattice parameter. If I say very correctly, what is the lattice parameter? Like some metals like copper or aluminum, like 4.04 angstroms. like uh, like 1 nanometer is how many angstroms? 1 nanometer is called 10 angstroms. Like, so if we have 4 angstroms of bond length, so how many atoms you can accommodate? Only 2 to 3. That's it. So the same thing that is happening, like 10 atoms you can accommodate. So the same thing is happening once if once if I start decreasing the size of the particle. I mean, if you're talking in the nano regime from 20 nanometers to 5 nanometers, or 5 nanometers to 1 nanometer, see, the fraction of surface atoms that are available on the surface drastically increases. But the same goes if I move back. Like if I'm moving back, what happens? The number of atoms inside the bulk started to decreasing. That means the fraction of atoms in bulk started to increase if I increase the surface area, if I increase the particle diameter or the size of the material. Now, um, so why we are doing this? I mean, if you're decreasing the nanoparticle, if we're reducing the size of the nanoparticle, that is good. Then why we are doing it? So there must be some properties that are attracting or more attractive when compared to the properties in bulk. So one of the thing is the surface plasmon resonance. So what exactly happens in surface plasmon resonance? So see, there are three terms. One is bulk, surface. Second term is plasmon, and the third one is resonance. So there are three terms. One is surface, another is plasmon, and another is resonance. So what is happening? So what exactly mean by these three terms? One is the surface. I mean, we are talking about the surface. I mean, we are talking about the surface atoms. The atoms, for example, if I take a, for example, sorry, for example, if I take a nanomaterial or a quantum dot, for example, which is let's say it's not a quantum dot. Let's say I have a spherical nanomaterial, which are a gold nanomaterial of a size like 10 nanometers or 20 nanometers, for example. I take, yeah, for example, if I take 20 nanometers, so what is happening? So the first term is surface. So I'm only talking about the surface atoms. And we can talk about the bulk atoms, but this phenomena is only related to the surface atoms. So I'm only talking about the surface atoms. Next, plasma. See, uh, uh, in plus one or plus two, you have heard like collective oscillations, like how a wave oscillate. Like if you take a rope, to what is happening. If you just jerk one side, the wave travels. So there are things that are oscillating. So plasmon is nothing but the collective oscillation of electrons. So for example, I have like one electron, two electron, three and four. So what is happening? They're collectively oscillating. So these electrons, they're collectively oscillation. So the plasmon is nothing but the collective oscillation of electrons. So the surface is nothing but the atoms, or we are talking about the thing, maybe anything, the atoms or electrons or anything. We are only interested in surface. Next, the plasmons. That means the collective oscillation of electrons. So plasmon is nothing but the collective oscillation of electrons in surface. That means the collective oscillation of electrons at surface. Next, the resonance. I mean, you have done many of people have done the plus one and plus two level grades, where we did the resonance testing or the resonance frequency to find what is the frequency in open tube or closed tube. So the same thing. The resonance is nothing but if two mediums are oscillating, if if they have frequencies like integral multiples, then we call, if they are oscillating in integral multiples of the frequency, then we call it as a resonance. So the same thing is happening. So so, uh, so what is the total term? Surface plasmon resonance. So the surface plasmon resonance is nothing but the collective oscillations of electrons on the surface because of the frequency, or because of some external energy. What is here the external energy? The external energy is light, or we call it as a photon. And we all know, again, from plus one standards, we all know photons have some energies. And photons or light travels in a wave path. So if it has a wave path, then it must have frequency. So every photon has a certain frequency. So depending upon the frequency, electromagnetic radiation has a very broad range, from like radio waves to visible range to UV rays to X rays to gamma rays. These are electromagnetic radiation, or we compare it to the photons, but only the difference is in the frequency. So yeah, for example, if we have a light, and let me show you. Let's say this is our surface, and for example, the light is falling on the surface. I mean, that is the photon. The photon has an energy. Each photon has an energy that we call it as h nu. What is h? H is a Planck's constant. Nu is a frequency. So every photon, like if I assume photon one, it has an energy h nu. So what is h? Planck's constant, and mu is frequency, or we can even write frequency as speed of light divided by wavelength. The speed of the photon, and the speed of photons are nothing but light. So the speed of photon is equal to speed of light, that is hc by lambda. So shorter the wavelength, higher is the energy. Higher the wavelength, lower will its energy, and vice versa. The frequency and wavelength relations are also same. They're inversely proportional. If you have a high wavelength, you have low frequency. If you have low frequency, then you have high wavelength, or high frequency, then you have low wavelength. So coming back to a plasma resonance, so if a light falls on the surface, so what does it do? If for example, if I have a bulk surface and light falls on the surface, so nothing much can be obtained if I reduce the size of the particle and make the particle, or make the material in nanoscale. For example, the gold nanoparticle, if I made it 20 nanometers, and if I show the light on it, so what happens? See, the wavelength of the light, for example, if I'm using like violet, I guess it has 200 nanometers of wavelength. And if I have a nanoparticle of like 20 nanometers, so what is happening? The size of the diameter of the nanoparticle and the wavelength of the light are comparable. Or you might say the wavelength of light is much greater when compared to size, not much greater. It is somewhat greater when compared to the size of the nanoparticle. So what happens then? See, if if my size of the material gets decreased, then what happens? See, if my size of the material gets decreased, there is a picture of density. Then I will just give a little bit of taste. So there is a theory. There is this thing of density of states. When you reduce the size of the particle, the density of states, I mean the allowable energy of the electrons will get dispersed. Uh, it's just a thing just I want to say. So let's move on to this. Now, what is happening in surface plasmon resonance? So once this light falls on the surface, what happens? These electrons will oscillate, and if one electron takes an energy and it goes to the higher states. Now, what happens to the nucleus, which is pulling those electrons? So once the electrons moves or have a higher energy and oscillates at this position, so it the due to electrostatic due to the electron and nucleus. Electron has a negative charge, nucleus has a positive charge. I shouldn't say nucleus. Nucleus has protons and neutrons. Because of protons, you have positive charge. So because of electron and protons, you have plus and negative. Once the light falls on electron, the electron will move, and according to that, nucleus tries to pull it. So there is an positive and negative fields that are creating, or you can call it as a dielectric, where you can see here. Here there is a production of plus and minus. It's like a production of dielectric. Now, Because of this, there is an oscillation. Once the It's not like one photon falling on the material, right? There are a number of photons falling on the material, and because of this, we have an oscillation. And if the electrons takes enough energy, like enough amount of quanta, and then they oscillate like this. If suppose this is an electron cloud, or we can say, for example, I will draw it. See, here it is a material. Sorry, material has plus, minus, plus, minus, plus, minus. So material consists of atoms. So atoms has protons and electrons. So once the light or photon falls on the electron, it excites it. It excites it. So once the electron cloud, this is called as an electron cloud. So this whole electrons is called as an electron cloud, because these electrons are like delocalized. They are not like 1s2, 2s2. These are not electrons that are explicitly localized. They are not localized, so they are called delocalized electrons. They just move randomly, just like electron cloud. Clouds move randomly in the sky. So the same thing is happening, not randomly. It happens because of air. So let's just say it moves randomly. So the thing that happens is the electrons move randomly inside the solid. So now, once the light falls on the electrons, they starts oscillating. Once one electron starts oscillating, it pulls another electron and another electron. So they starts oscillating. So you can see this is an electron cloud. Because of this dielectric, there is a production of electric field, and this electric field, we have a radiation, which is electromagnetic radiation. Because of this oscillations, we have electromagnetic radiation. Now, everything is okay. Once the light falls on the material, atoms and electrons, the electrons, the delocalized electrons, starts to oscillating. This oscillation leads to electromagnetic radiation. So what is happening? Electromagnetic radiation again. So here you can see, for example, this has like 10 nanometers, this has 15 nanometers, this has 16, this has 19, this has 20, this has 24. So I'm just giving an example. So what happens? I have different sizes of nanomaterials. Here I have like 20 nanometers, here I have 19, here 18, 17, 16, 14. So I have different sizes of nanomaterials, and when I just show a light on it, they glow, and they're glowing in different colors. Why? Because, see, depending upon their size, the electron, depending upon the size of the nanomaterial, the electrons are distributed differently on the surface. So if we have a different sizes, there is a different distribution of electrons on the surface of the atom. So that is the reason why we have different colors. We have different colors because of different sizes of the nanoparticles. That's what is happening. So SPS is SPR, the surface plasma resonance is like the collective oscillation or collective oscillations of electrons because of in resonance with the light that is falling on it. And depending upon the size of the depending upon the size of the nanoparticle, like larger to smaller, the electron distribution on the surface changes, and because of this, they excite at different frequency. Just like I have said before, if electrons are oscillating very vigorously, very with very high frequency, then what happens? If you have very high frequency, you will get a violet color because violet has a low wavelength. So higher the oscillations, higher the collective oscillations of electrons, higher will be the lower will be the wavelength, and lower the wavelength, we are going towards the violet color, the VIBGR, VIBGYOR, the rainbow color. We are going towards the lower wavelength regime, so the violet color comes. Now, what happens if this collective oscillations is very slow? I mean, it has a not slow. It has very low wavelength, not very low. It's like a low wavelength. Then high wavelength. Then what happens? If you're talking about the high wavelength, then we have low frequency. Then we are going towards the red. So that is what happening. Sorry, that is what happening. So we are going towards red. See, we are going towards the red. What is happening here? The frequency of electromagnetic radiation that is coming from quantum dots because of quantum dots, sorry, not the nanoparticles, due to surface plasma resonance is increasing. So if we go from here to here, there is an increase in wavelength. That means the red color, we have electromagnetic radiation of red color. But if the collective oscillations are very vigorous, it has a very high frequency, low wavelength, then we are going towards the violet wavelength. So this is about surface plasmon resonance. So I guess I have covered all the topics that will be helpful for you in solving the assignment questions. So yeah, that's it. So Samrat, sorry, yeah. I guess three have joined. So you three people, if you have any doubts, please ask now. If you have any doubts related to like topics or any, so far I have explained. Hello. Yeah. Okay. Sure. Sure. Please, if you have any doubts, you can ask or you can just write in chat so that I can read and explain. Yeah. Yeah. Please go ahead. Please go ahead. Please go ahead. Okay, sure. You don't have any doubt. Okay. So, if there is any problem dealing with assignment questions like uh, there are concepts that you people not able to understand. I know it is just a second lecture, but still, if there is any confusion or anything that needs to be explained, please.